Earthquake prediction has long been one of the most elusive goals in earth sciences. A statement from a prominent geologist once summed up the challenge. If there's ever going to be a Nobel Prize in geology, it will be awarded to the person who figures out how to predict earthquakes. Earthquakes are among the most destructive natural disasters, causing massive loss of life, infrastructure damage, and economic disruption. Despite over a century of research and technological advancements, scientists have yet to develop a reliable method to predict the time, location, and magnitude of an earthquake. Traditional methods of prediction based on geological surveys and historical data have provided only limited success. With new advancements in artificial intelligence, particularly machine learning, there is now renewed hope that we might be able to foresee seismic events with greater accuracy. Machine learning is opening up new possibilities for understanding the complex behavior of faults and, potentially, forecasting when the next big earthquake will strike. The challenge of earthquake prediction. Earthquakes are a sudden release of energy in the Earth's crust, which generates seismic waves. These waves cause ground shaking that can lead to disastrous consequences, such as building collapses, landslides, and tsunamis. The aftermath of a major earthquake can be devastating, with over 1.3 million people having died from earthquakes in the past century alone. The deadliest earthquake on record, the 1556 Shaanxi earthquake in China, killed approximately 830,000 people. Despite the significant social and economic costs of earthquakes, the ability to predict when and where one will occur has remained out of reach. The primary difficulty lies in the complexity of the Earth's subsurface and the unpredictable behavior of tectonic plates. Traditional methods focus on studying fault zones, monitoring the release of seismic waves, and analyzing past earthquake data. However, these methods fail to provide reliable predictions because of the irregularities in fault movement and the deep unpredictability of seismic events. Over the years, various hypotheses have been proposed, such as the idea that lunar phases or planetary alignments influence seismic activity, but no scientific evidence has consistently supported these theories. As a result, predicting the exact moment an earthquake will strike remains a significant challenge. The role of machine learning in seismology. The rise of machine learning has brought new tools and methodologies to the field of earthquake research. Machine learning allows algorithms to sift through vast datasets, identify patterns, and make predictions. Earthquakes, by their nature, involve complex processes that generate large amounts of seismic data. Traditional analysis methods were unable to process the sheer volume of data quickly enough to detect potential patterns. However, machine learning's ability to handle big data efficiently and spot minute trends has made it a promising tool for earthquake prediction. One of the key advancements has been using machine learning to analyze seismic signals, which are often overwhelmed by noise. For decades, researchers discarded the small seismic events, or micro-earthquakes, that occurred in the laboratory as irrelevant. But ML has shown that these seemingly insignificant events contain valuable information about the behavior of fault zones and the likelihood of a larger seismic event. A study by researchers at Penn State University, for example, revealed that using NL to analyze seismic data from an earthquake machine, a controlled laboratory setup, could accurately predict when the next micro-earthquake would occur by detecting patterns in the frictional behavior of the fault. With machine learning, researchers have been able to analyze 100% of the data from experiments, whereas before, only the most obvious events were considered useful. The earthquake machine, a step toward understanding faults. To better understand the dynamics of fault zones, researchers have utilized specialized equipment like the earthquake machine. This laboratory apparatus is designed to simulate the frictional sliding of fault zones under controlled conditions. It consists of two hydraulic cylinders that apply force to a fault zone, causing it to slip in a manner similar to the movement of tectonic plates in the Earth's crust. The machine records the acoustic emissions produced by the frictional sliding, which are essentially micro-earthquakes that occur as a result of the fault slipping. The data collected from these micro-earthquakes in the lab is invaluable for understanding the underlying mechanisms of seismic events. By studying these acoustic emissions, scientists have learned about the fundamental properties of fault behavior, such as how faults build up stress over time before slipping. The use of the earthquake machine has proven especially valuable because it allows for precise control over experimental conditions, making it easier to observe patterns in fault motion. This allows researchers to develop a more comprehensive understanding of the factors that contribute to larger seismic events. Furthermore, machine learning has enabled researchers to predict the occurrence of these micro-earthquakes in the lab with surprising accuracy. For example, algorithms trained on data from the earthquake machine were able to predict the next slip event with great precision, a breakthrough that has the potential to translate to real-world earthquake prediction. Scaling the model. Can machine learning predict earthquakes on Earth? The challenge, however, is scaling this predictive capability to the much larger, more complex systems found in nature. Unlike laboratory experiments where conditions can be controlled, real-world earthquakes occur along fault zones that stretch thousands of kilometers across the Earth's surface, and seismic events are not as frequent. In fact, most earthquakes occur on timescales ranging from decades to centuries, making them incredibly difficult to predict. Despite this, researchers have identified certain types of seismic activity that occur over longer periods, such as slow slip events, which might provide a breakthrough in prediction models. Slow slip events are a type of earthquake that occurs gradually over days, weeks, or even months, rather than in an instant like traditional earthquakes. These events, though not as dramatic, involve significant movement of tectonic plates, and their behavior has been closely studied in locations such as Vancouver Island, Canada. Researchers used seismic data collected from slow slip events beneath Vancouver Island to train machine learning models, and the results were encouraging. The machine learning algorithms were able to predict when these slow slip events would occur, based on the seismic signals recorded in the data. Remarkably, the same algorithms that were successful in predicting micro-earthquakes in the lab also worked with slow slip events, indicating that machine learning could be applied to natural seismic data. This breakthrough offers hope that ML could eventually be used to forecast larger, more catastrophic seismic events by studying the subtle, gradual changes in the Earth's crust. Limitations and future possibilities. Despite the promising results from laboratory experiments and slow slip events, there are still significant limitations to the current predictive models. Most notably, the timescales involved in earthquake prediction are far longer than those typically encountered in machine learning applications. Machine learning excels in scenarios where data is abundant and timeframes are relatively short. But predicting seismic events that may occur over the course of decades presents a unique challenge. For example, earthquakes in major fault zones like the San Andreas Fault or the Himalayan belt may occur infrequently, with some regions having not experienced a significant quake for hundreds of years. As a result, predicting the exact timing and magnitude of such events remains an ongoing challenge. Additionally, the complexity of the Earth's interior, including variations in rock properties and fault dynamics, makes it difficult to account for all the factors that influence earthquake behavior. While machine learning models have shown the ability to predict slow slip events, predicting large, catastrophic earthquakes that release enormous amounts of energy remains a distant goal. That being said, researchers are optimistic that with continued advancements in machine learning techniques, such as deep learning and neural networks, more accurate predictions may be possible. These more advanced algorithms could analyze vast amounts of geophysical data, including temperature, pressure, and fault mechanics, to provide a more complete picture of earthquake behavior. That's all for today's video. If you found this video interesting and informative, don't forget to give it a thumbs up, and make sure to subscribe to our channel for more exciting updates. Hit the notification bell so you never miss an episode. Thanks for watching, and we'll see you in the next video.